Hello everyone, I am Dr. Vasagari Krishnasree, working in EC department of VNR VJYT. So today I would like to explain about Class B power amplifiers, and in the previous videos I have explained about introduction to power amplifiers as well as Class A operation and its derivation. In this video I will cover the Class B power amplifiers. The contents I am going to cover are the two types of Class B power amplifiers and comparison of the both and introduction about our need of Class AB and Class C power amplifiers. First we will see out of two varieties of Class B amplifiers. One is Class B transformer coupled amplifier, another is Class B complementary symmetry push-pull amplifier. So let us take the circuit diagram of Class B transformer coupled power amplifier. As the name indicates, the input is taken through transformer and output is also taken through transformer. Here there are two sections, one is upper section and another is lower section. Why these two sections are required? It is depending on the load line and the operating point. If you look at the load line of Class B power amplifiers, the operating point is located on cutoff line or at cutoff. The point is VCC and 0. That is VCQ is VCC and ICQ is 0. So because of this one, when you are applying an input signal, so the input signal is not covering on the any part of the load line. That's why this is being eliminated when it is coming onto the output. So here you can get only the positive peaks of this transformer coupled amplifier. So whenever there is a negative half cycle, so then it becomes minus plus minus plus. So in the negative half cycle, Q2 will be on. In the positive half cycle, plus minus Q1 will be on. So I can say during the positive half cycle, transistor 1 is on. During the negative half cycle, transistor 2 will be on. Suppose if I am not using the lower one, only one positive cycle will come. If I don't use the upper one, only the negative half cycle will come. So these waveforms are indicating that because of this operating point is located on cutoff frequency, either positive half cycle, suppose if you are applying only negative half cycle is coming onto the Q point, then it gives only the negative half cycle. So because of these two sections, top section is working for the positive half cycle, bottom section is working for the negative half cycle. Otherwise it gives only for the 180 degrees. So the angle of conduction of transistor is for 180 degrees. That's why it provides either positive half cycle or negative half cycle. If you combine both, then we are going to get both the half cycles. That's why two sections are required and the operation is as usual as Class A. So here two Class A amplifiers are divided into two halves and operating point selected is on cutoff. So it is providing only half of the portion of the input. That's why the input is not resembling the output. If you provide the other section also, then we can get the other side also due to these two sections. So but as a default, it provides only half the half cycle. That's why input is not resembling the output. It provides lot of distortion. So this distortion, we call it as harmonic distortion. And one more distortion is also coming into picture. That is, suppose whenever you are taking, so instead of this one, 180 degrees, suppose positive half cycle, the transistor 1 is conducting, but before conduction there is a small gap like this, and even for the second transistor again there is a small gap. This gaps coming due to the cut-in voltage of transistor. For a silicon transistor it is 0.7. So due to this cut-in voltage, whenever the voltage appearing at the base of Q1 transistor is more than 0.7, then only Q1 is on. Similarly, for Q2 also it requires minimum of minus 0.7 voltage so that it is operated. Because of this center tapping coupling, this minus 7 is becoming plus 7. So this minimum of 0.7 voltage threshold is required. Some kind of distortion is appearing, we call it as this is first distortion due to not resembling the input. It is known as harmonic distortion. And the distortion due to this cut-in voltage, we call it as crossover distortion. So these are the two distortions available in class B power amplifiers. Next we will see that crossover distortion. You can see very clearly here, you can see. So this crossover distortion is due to cut-in voltage of both the transistors in both the half cycles. This Q1 and Q2, this is second version. It is class B symmetry push-pull power amplifiers. So here there is no transformer will be used for coupling. But how you are going to get that inversion of signals, because one transistor should work for the positive half cycle, second transistor should work for the negative half cycle. That inversion of signal is provided due to the transformer in the previous one. Now it is not having any transformer. That's why this Q1 and Q2 we are selecting complementary to each other. That is, if you take Q1 as PNP, Q2 you can take as NPN. So these are complemented to each other. And similarly, above half section will be used for negative half cycle, below half section will be used for positive half cycle. So that's why the resemblance of input and the output can be avoided by using two sections. And input is provided through coupling capacitor, which going to block the DC voltage. And whenever it is a positive half cycle is going to Q2 transistor, then Q2 will be on, and negative half cycle Q1 will be on. So this positive half cycle is produced due to Q2 on, negative half cycle is produced due to Q1 on. So for both the half cycles we are appearing the output, but due to that cut-in voltage effect, then there is a, wherever the crossovers are available, that is whenever the at zero crossings there is a small tilt will be observed. That tilt is created as crossover distortion. So for both the class B, two types, transformer coupled and complementary symmetry couples, we require two sections for positive cycle and negative half cycle, so that by combining these two, here the load is taken at the emitters where they are connected together. So for the above Q1 transistor there is a negative power supply required, for below transistor there is a positive power supply required, because NPN transistor will work on positive, PNP transistor will work on negative power supply. So this is the operation of class B. Now we have to see the conversion efficiency. Conversion efficiency is already defined as, for a given DC power, how much it is converted into AC power into 100%. So now we have to see how the conversion efficiency will be derived for this one. Now let us take the load line I am considering. So it is VCC comma 0, x-axis is VCE, y-axis is IC, and all these things, the Q point is located at this point. So whenever you are providing VCC, so now we can consider PDC as, there are two sections for positive half cycle, that is it is VDC into IDC. So VDC we are providing as VCC, and IDC is due to two sections, because it is a half wave rectifier. IDC is Im by pi plus another half cycle, it is Im by pi. So because already we know for an half wave portion, IDC is whenever this is kind of thing for half cycle, okay, this is I, this is T. So IDC, it can be measured from the previous knowledge, it is Im by pi. So there are two sections are available. For one section it is Im by pi, second section also Im by pi. Then this becomes VCC into 2 Im by pi. This is our PDC of class B power amplifier which we are giving. Then coming to the PAC. So PAC is PRMS, that is we have to take PRMS into IRMS. So because we are having for both half cycles, the complete I out will be, it is containing full waveform. Full waveform means IRMS will be Im by root 2, because for a full sine wave you can compute this IRMS and VRMS. Similarly for VRMS it is Vm by root 2. So PAC becomes Vm by root 2 into Im by root 2. So this becomes Vm into Im by 2. Then whenever we are applying some signal on this one, so I am applying a signal. So here I am applying a signal like this, input signal. Okay. So it is transformed onto the output like this. Okay. For this is a load line, it is drawn for one half cycle. Same will be applied for the second half cycle also, like this. So it will go only half cycle it will come. So what is the, here it is ICQ. What is the maximum swings we have to derive for this one. So maximum swing, I will take another color which indicates what is the maximum swing. Okay. So I am considering this as the maximum swing, and negative half cycle it is not considered. This is the maximum swing. So I am drawing what is the minimum and maximum. This is I maximum. So here it is V maximum. Okay. So PAC is equal to Vm into Im by root 2. Then conversion efficiency is considered as PAC divided by PDC. That is PAC is Vm into Im by 2. So PDC is VCC into 2 Im by pi. So this will, what is the maximum? Maximum, if you consider efficiency maximum, this into 100%. This is the efficiency. So maybe you can cancel out. You can cancel out Im and Im. So Vm. So finally this becomes Vm into pi by 4 into VCC into 100%. Then to compute the EC maximum, so what is the maximum? It can go up to, so the minimum value is 0, minimum is 0, maximum is, so this is the V maximum. It can be, maximum is VCC. So it cannot go more than this one. So for maximum value, Vm becomes VCC for maximum value. So efficiency derivation becomes Vm is equal to VCC. Then it becomes pi into VCC divided by 4 into VCC. That is into 100%. So it becomes pi by 4. Pi by 4 means 78.5%. So if you compare this efficiency with class A efficiency, conversion efficiency maximum is, for the class A, it is 25 to 50%. It is increased to 78.5%. So maybe class A, basic difference between class A and class B. In class A, Q point will be in the center of load line, that is active region. So here only the difference will come. In class B, Q point will be on cutoff. That is, transistor will work for 360 degrees here, it work for 180 degrees because we are using two sections. Because of this, transistor is operating for only half the time, but here transistor is working for full time. So it is something like the transistor is consuming most of the time, most of the cycle. So the power consumed by transistor will be more. Power consumed, it itself is consuming more power, consumed more. But here only half the power is consumed. That is, this remaining half power, it is being delivered to the load. So because of this less conduction of the transistor, more power which is reserved by this half of the conduction, half of the consumption will be reduced. That half will be transferred to the load. That's why efficiency here, minimum 25 to 50% conversion efficiency has been increased to 78.5% efficiency. So that's why class B is, but what is the problem is, if you are using only one section, it is giving only half cycle, but we are using the two sections which is known as push and pull. That is, for positive half cycle it is pushing, negative half cycle it is pulling. So that's why we are observing for both the half cycles but with a crossover distortion. So distortion is available in both the cases. What is the distortion? Input is not resembled as the output. So here it is only half cycle, another half cycle also will be taken, and crossover distortion is another distortion is available. Because of the push-pull arrangement, harmonic distortion is eliminated, but crossover distortion is still remaining. Because of this class B and crossover distortion, we have to increase the efficiency still further. Then we have to use class C. If you want to reduce the crossover distortion, then this is crossover. Then we have to go another combination which is known as class AB. So now here the introduction to why we require class C and class AB is to avoid crossover distortion we are going to AB, and to avoid harmonic distortion we are taking the push-pull configuration. Then we will see the derivation I have given in a different steps. IDC is 2 Im by pi, PDC is 2 VCC by M by pi, VRMS Vm by root 2, IRMS Im by root 2. This is IRMS is Im by root 2. So PAC is Vm by 2. The derivation of conversion efficiency is PAC by PDC, it is pi Vm by 4 PCC. Only the maximum value it occurs when Vm reaches the VCC, then it becomes 78.5%. So there are two versions of class B. What are the differences? Also is important. If you take the push-pull transformer coupled amplifier, we have to use both transistors are similar. Either NPN or PNP you can use. For one half cycle, one NPN will be used or one PNP will be used, and the center tap transformer is providing that inversion of the signal so that we can achieve for both positive and negative half cycles. Here transistors are of not same type, it's complemented to each other. Second difference is input and loads are connected through the transformer, but here no transformer is used. So because of the transformer is avoided, the heaviness is avoided, and losses of transformer also is avoided. Okay, impedance matching is possible due to the transformer. It has to match with the loudspeaker. That's why transformer matching will give you a perfect matching. But here impedance matching, it is not so perfect, but it is taken through a common collector mode. Still it provides low output impedance so that it is matches with the loudspeaker. And frequency response will be poor because of the usage of transformer. Here the frequency response has been improved, and the circuit is heavy, bulky and costly because of the transformer. But here, as transistors require less space, it is not heavy, not bulky and not costly. And dual power supply is required in this case, but no dual power supply, only one power supply is required for the transformer coupled. So we can have both advantages of disadvantages with the two configurations. But normally complementary symmetry push-pull amplifier will be best option for the class B power amplifiers. because it is providing all the advantages like less space, less cost, and less bulky. So this is about derivation and operation of Class B power amplifiers. These are the references are used for preparing this video. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.